to the next talk, which is by Miljenko Cemeljic, and it will be about flux ropes in SANE disks.
Thank you. So I'm sharing my slides. You see it? Everything okay? You hear me well?
Yes.
Okay. So good afternoon. I'm Miljenko Cemeljic from CAMK in Warsaw. And I will show you some preliminary results from work which I did as a visitor in Shanghai during the last 8 months. I just came back from China in the group of Professor Feng Yuan in Shanghai Observatory. This was the PIFI scholarship, or this Chinese Academy of Science scholarship given for me to work in Professor Feng Yuan's group. So I will speak about flux ropes in SANE disks. A little bit of introduction. I should do this way, you will see better. And yeah, you see my slides, yes? Okay, so I will show you some results, preliminary results from full 3D simulations and formation of magnetic islands and flux ropes. And I will speak a little bit about reconnection layers. So as an introduction, the motivation for this research were episodic jets. So in the accreting systems, large scale jets are usually steady, but episodic jets, which we observe, are sometimes related to flares, and those are observed on the smaller scale. So one example is Sagittarius A, which is the massive black hole in the galactic center. We observe radio, infrared, X-ray flares several times a day. Conclusion from those observations was that delays in peaks in the light curves and their fast rise and slow decay in the brightness and polarization are related to the ejection and expansion of plasmoids. We also see knots in the jets, like in 3C120 and M87, and this also could be related to episodic emission. So for these steady jets, there are models like Blandford-Naik and Blandford-Payne for these continuous jets, but for these episodic emissions, episodic jets, we still don't have a generally accepted model. So one of the, in this publication, Yuan and et al. 2009, there was a proposed model which was in analogy with coronal mass ejections from the sun. And here you see on the right side, you see the figure from that publication. So the closed magnetic field lines emerge from the main body of the accretion flows, and they are expelled to the corona region. The foot points of these loops are positioned in the turbulent accretion flow below, yeah? And then the twisting of these lines results in reconnection, and then the flux ropes are formed. Magnetic tension force will be weaker in such case when the reconnection works, and the initial equilibrium between the magnetic tension and magnetic pressure is not maintained. The flux ropes will be accelerated outwards, and they will form the episodic jet. We see flares from such thing. So this was one model from 2009, and recently, so 10 years later, in Shenda et al., there was suggested another model also to model the coronal mass ejections, which used the analogy with toroidal instability, and this was applied something from tokamak research. So these two models, and I will deal with the first one. So what was simulated in 2D? There were simulations in this year, presented in 2D ideal GRMHD simulations, and this was done with the black hole accretion code by Port et al. And this was with adaptive mesh refinement, and they simulated both MAD and SANE disks, which are obtained with the different initial magnetic field configurations. As you see here, they did 4 models in which you have loops. The red are loops of the magnetic field, and blue also, but blue are in the different direction. So combining the loops in a different way, they were obtaining different results. And they were, in fact, since they had MRI, idea was with the loops simpler and less dense, they will get more or less turbulent medium. So we see results in A, B, C, D case below, and we see the differences. So the results here I show B phi, so toroidal magnetic field. And one thing which is interesting, I mean, important to notice here is the resolution in which I wrote here the resolutions. So these are high resolutions, and they can resolve well the plasmoids, the substructure, let's call it for now, the substructure in the flows. So we see that in these 4 cases, there will be different substructure. They are following one of the plasmoids, what they call plasmoid here. So I will show simply one of the blobs, we could say, and which are follow in time. They move outwards. And you see on the left side here, there is this plasmoid going from below, from the bottom, upwards and radially outwards also, you can see. So this plasmoid is followed in time, evolving. And then on the right side, there is a 3D reconstruction. They do axisymmetric simulation. And if you imagine that you rotate the phi plane, then azimuthal plane, then you can construct the 3D trajectory of such a plasmoid. These were ideal MHD simulations. So the reconnection was, which obviously happened here, was numerical. In a little bit later was presented the similar with the same code, but resistive simulations. And the setup was similar, like in this, what I showed before. And the resolution was large because they were using a small ohmic resistivity. They were using a small resistivity to see if the ideal MHD results are converging. I mean, if this small resistivity results are converging to the same picture like in the case of ideal MHD. And yes, they conclude. Here I am showing the magnetization. Magnetization is written down at the bottom in the caption, B square over rho. And the snapshots in quasi-steady state phase of accretion in SANE case are shown here. And they see in magnetization that current sheets along the jet sheet are in the relativistic regime where sigma is much larger than 1. And in the disk, so along the equatorial plane here, they are in the trans-relativistic regime. So for me, I mean, why I'm showing this, simply that the ideal MHD results and the slightly resistive MHD results were showing the same physical picture, and here in the same case with the plasmoids forming and going outwards. So in Professor Feng Yuan's group in Shao, PhD student Hai Yang performed simulations using the Athena ++ in full 3D. So simulations I showed before were 2D axisymmetric. Here it's full 3D, and in this we are, Hai Yang simulated ideal MHD, no resistivity here. So that's why it was important for me to see if ideal MHD and the little resistive will show qualitatively similar results. So now in those simulations, we cannot, since it's 3D, we cannot have so large resolution. So we are at 700. Remember, there was 600 something, 6,000, sorry, something, as you see in the upper part of, in the text in the upper part of the slide. Now we are having 700 times 256 times 128 in spherical coordinates. And here there is no AMR. Here is the staggered mesh constraint. Here is the statical grid, static mesh refinement used for the grid. And the CT, the constraint transport, is used for divergence free. And the same was in the previous simulation. So here you see on the bottom, you see the figures with structure of the grid. On the left side is the large grid, large scale here, and in the right side is the inner part of the grid, static grid refinement. And then we have initial conditions. Hai Yang did simulations in those cases which are here in the table, but yeah, here I'm showing only the results in MAD simulation. Sorry, I made wrong. So SANE 00, this line, the red should be above. It's shifted somehow. So SANE 00, it means SANE simulation without rotation of black hole. And you see the structure of magnetic field, initial structure of magnetic field here, and the density. So evolving this, here are the results in a slice at one plane, in one azimuthal plane. And I'm explaining here how I am measuring this, what I will show later. So I'm capturing with, maybe better will be, so here is the density. The black line in color density, the black lines are streamlines with magnetic field, poloidal magnetic field, and the arrows are for the direction. Here I'm showing the evolution following with the black and red in the crossing of the black radial line and the black circular line. You can see there is a plasmoid, there is a center of the plasmoid. So I am following such plasmoids in time. Here it will be better visible. On the left side is a plasma beta. And so because I need to measure how this plasmoid moves. So how I will do it, I will just mark it, and then I will write down the parameters. I will write the velocity, the position. And then on the right side, you see the results. This is the time dependence of the two plasmoids here still, because we are cutting in the plane. So in the two plasmoids, one, as I said, is on the crossing of black circular and radial line, and other is on the red. And I'm following on the right plots these two plasmoids. On the top panel is shown position in time. Radius you see in y-axis, and from this I can get the velocity, yes. And in the bottom, I am having velocity of this plasmoid in time, how it is behaving. And it's interesting result that for both flux ropes, or for both plasmoids here, the average radial velocity is roughly 0.03 c. And this is something what was interesting to check, because in Feng Yuan's paper from 2009 and in the other papers, this is the velocity with which the plasmoids are moving. So in 3D, what the result in 3D matches what was anticipated. So here, what is in fact, what we are seeing, since we are now in 3D, these are plasmoids, which I was showing before in the cuts. But here, what I'm showing, it's a little bit busy, but it's in the same time. You notice the same time, but this, in the right corner of each panel is written different angle. In fact, this is the different azimuthal plane. And in the left side, if you follow the crossing of this radial and circular line, then you see that there is no plasmoid. On the middle and right one, there are plasmoid is visible, and these are in the different planes. So you can imagine that in fact, in the first one, we are not having, if you imagine the flux, let's say the filament going out of the surface of the disk, then you will have the flux rope. And here I'm cutting through in the middle panel, I'm cutting through the middle of such a rope. And in the right panel, I'm still catching this. And here what I'm writing in the caption, these are, by the way, these are poloidal magnetic field, and I am following the position of the minimum with this crossing of the lines. So I see that the plasmoid, in this case, in fact, the flux rope is somewhere between 7 and 70 degrees. It is still visible. So this is how I am trying to catch this flux rope by following its cuts. And then I'm constructing a plot on the left side here, how it is moving, how this middle of the flux rope, I was searching for the maximum, where about it was the widest. So this widest cut in the flux rope, I'm trying to catch it in the position in phi direction also, so in the different azimuthal plane, and it is moving radially outwards. And here on the bottom, it's now a different plot. So because I caught also in the one plot the spiraling of the middle of the flux rope. And on the right side, I'm trying to show it in 3D plot that it is spiraling around the central object, spiraling outwards. There is the trajectory of its center. Because now I have 3D simulation, I don't have to construct my trajectory, I can follow it. And this is what I am trying to follow here. Ejection of these flux ropes, because we see that it is going outwards. The center of this structure, which is footed in the disk, because when I follow this cross section of this rope, I see that it is starting in the disk and finishing in the disk, going in the phi direction, in the azimuthal plane. So I am here following it in the little bit more, because before I had just like 1,000. You see the times here were from 18,000 to 9.5. Here I'm following a little bit longer, from 20 to 40,000. And I am plotting on the right side the same, but it is now on the large scale. And we see, again, the same, I do the same trick. I follow the center of the, let's say, of the cross section of the flux rope where it is widest. So I assume it's the middle of it. And on the top panel on the right side, you see that this is what is the dependence on in time of such movement, proportional to time square. And velocity of this plasmoid or flux rope, in fact, here is also plot. And yeah, this is part of the analysis here. And we try to see how it will connect with the previous assumptions. And okay, reconnection will work here. And you see, follow this red line here, better in the right plot. There is a plasma beta. You see that there is some plasmoid, sorry, that there is a reconnection layer. And I'm following this reconnection layer from better, sorry, in the left point, in the left plot, you see in the crossing of black lines, there is one reconnection layer. And in the crossing of red lines in the left panel, there is another reconnection layer. So I am following this. I took here the bottom one, and I am trying, so this is the black one from the previous plot, the bottom one on the left panel, where is the crossing of the black lines. And you see, I'm analyzing the velocity, magnetic field along these coordinate lines, in fact, along the radial line, along the colatitudinal line. I'm projecting velocity, magnetic field, and forces. Centrifugal, here the lines are for centrifugal force, Lorentz, gravity, and pressure gradient. The most important here is that we have reconnection is in the middle panels here, that simply the magnetic field changes direction, as we see also from the arrows on the plot. So this is also part of the analysis to show that how the reconnection is working. But this is a numerical reconnection. I don't have resistivity. So this is the numerical reconnection. So from this previous slides, what I found that is this initial plot should be modified a little, that there is in fact forming another reconnection layer above the magnetic flux rope. And this another layer will help opening of the magnetic field lines. And in fact, it is helping the launching of such a plasmoid. In fact, flux rope in 3D, that it is breaking. And then you see we get the episodic emissions, episodic flare. So in summary, so these are preliminary results about the formation of magnetic flux ropes with Athena++. Magnetic structures which show as magnetic islands in 2D, sure, they can develop in some cases into the magnetic flux ropes in 3D. These ropes rotate and loop around the central object. And because of reconnection, ropes are pushed out of the disk surface and launched into the corona, pretty much similar like in the coronal mass ejections from SANE. Additional reconnection layer can form, not always forms, helping the launch of the rope. And this would cause episodic flaring from the vicinity of a disk around the black hole. So, thank you. Here is a picture which I did during the last months.
Mm-hmm. Thank you very much for the very nice talk. We have still a little bit of time for questions. So, yes, Agnieszka.
Hi, Miljenko.
Hello, hello.
Hello. Nice talk and nice results. I want to ask you actually, what is your opinion about the reliability of the simulations of magnetically arrested disks that are made in 2 dimensions only? Because from what I know is that the definition of the magnetically arrested disk is such that the magnetic flux on the black hole horizon is more than 10 or several tens times larger than the mass flux. So matter cannot accrete onto the black hole unless it finds some way around this magnetic barrier in the azimuthal direction.
Yes, and I would agree.
To agree. So how they can make a 2D simulation with this?
I think it's, I mean, practically they also did 3D simulations, but they were not publishing. I think simply because I think the logical way is, okay, let's see what we can do in axisymmetric 2D, and the 3D will be the really physical result. And another thing is, so this what you say is right, that simply near the boundary, you have to solve it somehow in 2D. So you have to just invent what is happening. In 3D, you would be looking what is happening. But problem was exactly this, what was hinted here. A reconnection will work. You will have magnetic fields, you will have reconnection. Is your ideal MHD code, which is usually faster, is it reliable, the result, or you need to do resistive MHD? And then I think this Riperda's work and he did also 3D simulation to compare, but he didn't show it yet. I think this was a preparation for the 3D work. So I wouldn't, let's say like this, I wouldn't believe to 2D simulations of MAD or any of those, in fact. To 3D, I would start to believe only when people discuss reconnection, compare, like in this 2D work was done from Riperda. And then if this similar work would be done in 3D, comparing resistive and ideal MHD, and then seeing what are the differences, then I would start believing. Until then, I would always be very skeptical, and I would say nice work. Even for my own simulations, I would say nice work, but yeah, has to be continued.
Okay, thank you. And another question is actually in your case, you have resistive 3D simulation, right?
No, ideal image. I said ideal.
The last one you showed was also ideal. So
everything was ideal.
Kind of a perturbation in the azimuthal direction in the initial state?
I didn't get, sorry, I didn't hear what?
I'm asking the initial conditions, yeah, what people do, they make a 3D run, but already at the time 0, they adopt
there was no need for that. There was, in fact, from what Hai Yang was, because I was not doing the simulations here, I was analyzing the simulations, but I remember that there was nothing about the perturbation in the toroidal direction.
Mm-hmm. Okay, thank you.
Okay, thank you very much. There is still a question from Maciek, so please.
Hi, so can you say anything already at this point about frequency of these flaring events or duration of those flaring events, any sort of characteristic like that, or is it too soon and you don't believe it and you don't wanna?
You know what, like this, since this is exactly what I was, you see this now I put on the slide. Yeah. So here in the long time, I was, but I don't know, this is 40,000 in these units of GR.
But could you guide me through this plot?
On the top panel.
Yeah.
So there is this position, and then in the bottom you have in the bottom panel is plasmoid velocity. So we see that radial velocity is kind of straight line here. And now a question would be, because I checked, let me show you, I checked all of those 4 groups of simulations. And I found, so as I say here, the red frame is wrong. It should be on the SANE 00. But I checked everywhere. Only in the case of SANE 00, I found plasmoids like here, that they are on the left panel here, you see, that they are atop the disk surface. And then they are ejected into corona. In these previous works in 2D, they were showing this along the jet, the plasmoids were formed. I didn't see it in 3D. This is why I took SANE only, SANE 00 simulation, because in MAD simulation, for example, I didn't see this substructure, but maybe this was not enough resolution. So what I would say, in 3D, episodicity, if it would be episodic, I didn't see it. And I would see the creation of such plasmoid, and then it would go out from the box. And I yet didn't see something where I would say, okay, it's a firm confirmation of period of formation, that, it will start on the left panel here, that it would start from, let's say, position 15, 20 or something, and that it would emerge and that it would be launched out. I didn't see this yet, but I was looking for that, and if I would see it here, I wouldn't be very skeptical. I would say that it would be quite realistic, let's say, for ideal MHD simulation. So I think those simulations already could discuss something like that when I find some such event.
Okay,
so I didn't find yet.
Because of course that would be extremely interesting from the Sergei star point of view, where we kind of have an idea how often the flares happen and what's the duration of a flare.
Yes, exactly. And as I say, I didn't yet find, but I did thousands of sweeps through the results, and then searching if there first for this what I am showing, I had really to find these cases where I could measure very nicely the velocities and positions, and that it would be really not disturbed by reconnection events meantime. But then to find more of those, I have some candidates, but I was not convinced, and then I didn't try to convince anyone else. Yes, but I think the simulations are already there. I'm here showing the smaller part. There is a simulation going up to 800. So yeah, it would have more time to evolve, and the new one would create, yes, and then we could see if there is a time if there is really some frequency of emerging of those. So I think simulations are there. Soon we should have it.
Thank you.
Thanks.
Thank you. If there are no more questions, I suggest